All right, today we're diving into a classic book, Algorithm Design, and we're going to tackle its very first big idea. And honestly, it's a bit of a curveball. It suggests that the most important part of designing algorithms, well, it has almost nothing to do with writing code. It's all about how you look at the world. So, let me start with a question for you. What could a huge, sprawling online ad system possibly share with a hospital that's just trying to figure out its staffing schedule? I mean, one's about clicks and making money, the other's about saving lives. They seem like they're from totally different universes, right? But believe it or not, they're actually built on the exact same core concept. And the answer is just that. It's a way of thinking. Both of these incredibly complex, messy, real-world challenges can be broken down and understood through the lens of algorithmic design. It's a framework for turning chaos into clean, structured, and most importantly, solvable problems. And look, this isn't just some abstract academic idea. This way of thinking is a super practical tool. It's being used all the time to solve some of the most concrete problems you can imagine. You know, what really connects all these different puzzles is a shared structure. That ad system, the hospital schedule, a communications grid, even a robot trying to navigate a factory floor. They can all be thought of as problems of managing resources flowing through a network. It's all about finding the most efficient way for stuff, whether that's information, people, or physical parts, to get from point A to point B. And once you can see that underlying pattern, you're halfway to building a real solution. And this is what leads us to the book's real core philosophy. It argues that algorithms aren't just there to give us the answers to problems. Nope. They are the very language we need to define the problems clearly in the first place. Just think about that for a second. The real magic isn't just cranking out a solution. It's the process of describing the problem so precisely that a solution even becomes possible. You know, they say framing the question correctly is half the battle. Well, algorithms give us the vocabulary and the grammar to actually do that. Okay, so to make this feel a little less abstract, let's look at a classic example that on the surface has absolutely nothing to do with computers. It's called the stable matching problem. So the goal sounds simple, but it's actually pretty tricky. We need to create pairs where there's no instability. Now, an instability is basically a recipe for drama. It's when a man and a woman who aren't paired together look at each other and both think, you know what, I'd rather be with you than my current partner. If that happens, they've got a reason to ditch their partners and form a new couple, which messes up the whole system. What we want is a perfect matching with zero instabilities. So the first step in building our language to solve this is defining the input. And for this problem, it's pretty simple. We just need a set of preference lists. Each man ranks all the women from his favorite to his least favorite, and every woman does the exact same for all the men. That's it. This simple table has all the data we need to untangle this whole messy social puzzle. So, how do we find a stable match? Well, instead of just randomly trying things, we can use this beautiful, simple procedure called the Gale-Shapley algorithm. It works in rounds. An unengaged man goes and proposes to the next woman on his list. If she's free, great, she accepts. But if she's already engaged, she compares the new guy to her current partner and sticks with the one she likes more. The other guy gets rejected and has to try again. This just keeps going, round by round, with men working their way down their lists until everyone is happily paired up. It's structured, it's methodical, and, as you're about to see, it's unbelievably efficient. And here's why that efficiency is everything. If you tried to solve this by brute force, just checking every single possible combination for just 10 couples, you'd have to sift through over 3.6 million possibilities. It's completely impractical. But our little proposal algorithm, it's guaranteed to find a stable match in, at most, 100 steps. That is the power of a good algorithm. It takes a problem that's basically impossible and turns it into a simple, manageable task. Now, the stable matching problem is just one example. It's one of many types of questions that we can frame and solve using algorithms. The book actually introduces a few other big representative problems that pop up over and over again in different disguises. But before we get to those, we need one quick bit of vocabulary: the graph. And don't worry, it's a simple idea. A graph is just a way to draw relationships. You have nodes, which are the things, and edges, which are the connections between them. Think of cities as nodes and highways as edges, or people as nodes and friendships as edges. It's a super useful way to visualize all sorts of problems. So our first big question is the one we just spent some time with: stable matching. You've got a bunch of preferences. How do you create pairs that are actually going to last? Okay, now let's switch gears from people to, well, infrastructure. The second question is all about cost and efficiency. Imagine you're trying to build a fiber optic network to connect a bunch of towns. You want every town to be on the network, but you want to use the least amount of cable possible to save money. That's the minimum spanning tree problem. From building networks, let's talk about getting around them. This next one is a classic, and it's famous for being incredibly hard to solve. You have a list of cities, and you know the distance between each pair. What's the shortest possible trip that visits every single city just once and then returns home? This is the legendary traveling salesman problem. Our fourth question is all about allocation. Picture this. You've got a bunch of jobs that need doing and a group of applicants. Each person is only qualified for some of the jobs. So how do you assign people to roles to fill the absolute maximum number of open positions? That's bipartite matching. And for our last one, let's bring in the element of time. Let's say you have one machine, like a supercomputer, that can only run one job at a time. You get a list of job requests, and each one has a specific start and end time. You can't do them all, so how do you pick and choose which jobs to accept to get the most work done? That is the interval scheduling problem. So we've got matchmaking, network building, scheduling. These 5 questions might seem totally unrelated on the surface, but they all point back to one single powerful idea. It's not about the specific puzzle in front of you. It's about the process of how you design a solution. At the end of the day, algorithm design is a creative process. It really is. You start with a messy, real-world question. You translate it into a precise, structured language, like using a graph, and then you design a step-by-step recipe that gets you to an efficient, correct answer. That, right there, is the heart of it all. Which really brings us to the final thought. A lot of the time, the biggest thing stopping us from solving a problem isn't finding the answer. It's finding the right way to even ask the question. So, think about it. What problem in your world, big or small, is just sitting there, waiting for the right language to unlock it?